Today's topic is on convolution. We discuss the convolution corresponding to signals and as well as the systems. So before going to the convolution, let us see how a sequence x of n can be represented with the help of n impulses. Okay. So we are introducing convolution, how to represent a sequence in terms of weighted and delayed impulses. Okay, you know that x of n is a sequence like this with positions of 0, 1, 2, minus 1, this is, and these values are holding some random values. So these are impulses located at 0, minus 1, 0, 1, 2 and minus 1 and individual impulses. So this impulse you can write with the help of del n, and this impulse you can represent it with del n minus 1, and this impulse with the help of del n minus 2, and this one with the help of del n plus 1. So let us represent a sequence x of n with the help of impulses. Okay. So any signal, okay, any signal x of n can be expressed as a linear combination of scaled and delayed impulses. So we see a sequence like this. Okay, and this position 0, 1, 2, 3 and minus 1, minus 2. Let us take, this is a sequence x of n. Okay. So all these individual values, okay, this is the value of x of 0, this is value of x of 1, x of 2, x of 3 and x of minus 1 and x of minus 2. So let us see how x of 0 was represented. So x of 0 was represented like this, 0, is x of 0, and this is represented as x of 0 and del n. With the help of an impulse, we are representing the value at position 0, x of 0, del n. Okay, and if we want the value x of 1, and this x1 is represented as x of 1 multiplied with del of n minus 1. Okay, with the help of impulse we have to represent that particular value. Okay, so already we defined that x of n can be expressed as a combination of scaled and delayed impulses. Okay, impulse have a strength 1 actually in general case. Okay, but we are scaling that impulse with its shifted version, that is n minus 1 is the delayed impulse, and when you multiply with x1, it one is scaled. So this value, okay, this value x1 is represented by using x1 and del n minus 1. Like this we represent the another value also, x2 also. okay, x2. So this x2 is represented as x of 2 del of n minus 2. Like this, you represent each and every value in the sequence, okay, each and every value in the sequence with the help of the scaled and delayed impulse. So you can write x of n as the linear combination of, okay, linear combination of this one, x naught del n plus x1 del n minus 1 del n minus 1 plus x of 2 del n minus 2 plus x3 del of n minus 3, right? And we have represented x minus 1 and x minus 2. So let us write those things also, plus x of minus 1 del of n plus 1 plus x of minus 2 del of n plus 2. So this, okay, these representation is the linear combination of scaled and delayed impulses. So if you sum up this one, if you take the different k values, okay, if you take in terms of summation, k equal to minus infinity to infinity x of k del of n minus k, okay. So you can represent xn in terms of, okay, you can represent xn in terms of the weighted and delayed impulses, okay. So this can be in the form of convolution, but actually, and this is referred to as an shifting property, okay. Shifting property means shifting property is x of n del n minus k equal to xk del n minus k. So this property, by this shifting property, shifts out the particular sample, okay. So this shifts out a particular sample or a particular value, okay. So x of n can be represented about, with the help of impulses by its scaled and delayed versions of impulses, okay. So why we are writing a particular value or particular sample like this, x naught is x naught del n, okay. Why means, if you write that x naught equal to, sorry, a particular sample x naught is not equal to xn del n, okay, but this is equal to, but xn del n is equal to x naught and del n, okay. So you should not represent a particular value, that is x naught, like xn and del n. You should write it as an x naught, sorry, xn del n should be written as x naught and del n, not equal to x naught, okay. So this is because if you write that y of n is xn and del n, okay, you write that yn equal to xn and del n, which is equal to, which is equal to a particular value. If you write it yn equal to x naught, this is a DC sequence with a value held by x naught, okay, that is a sequence like this, okay, having the values equal to x naught. So this is an improper, This is an improper representation. So you have to write like this. This one is the proper representation. Okay. So we have seen that xn can be represented with the help of scaled and delayed impulses. Okay, and this leads to the a representation of convolution. Okay, this is representation of convolution. Okay, in the aspect of signal, we are representing, we are using the convolution to represent a sequence xn. Okay, the same if you go for the system, in point of system, the point of system, we take a system like this and we are giving an input xn, we are getting an output yn. So if you give an input del n for the sequence, we are getting an output h of n. So here h of n is impulse response. If the system is LTI system, okay, for the given input del n, we are getting an output hn, which is yn, of course, and h of n is referred as an impulse response of a system, and an LTI system should satisfy the conditions of linearity and time invariance. Okay, an LTI system must satisfy linearity, that is we giving summation of inputs, different inputs like k equal to 1 to n ak x k n, and we are giving these inputs to the LTI system, and we are getting the outputs summation k equal to 1 to m ak y k n, and this satisfies the linearity. Okay, and this is linearity. Okay, and if you give a shifted input for the LTI system, we are getting our output y of n minus n naught, and this is time invariance. The time invariance property. If these two properties are satisfied by the system, then this plays a crucial role. This impulse response plays a crucial role for getting the response of any arbitrary input. Okay, let us see that. So seeing that for the del n, the output is h of n. Okay, and the system is satisfying for LTI system. For the LTI system, the del n is input, the output is h of n. Okay, now I give a shifted input del of n minus k. You are getting an output h of n minus k because it is going, it is satisfying the property of time invariance. Okay, for the del n input, the output is hn, and for the shifted del n, that is del n minus k, the output is h of n minus k. Okay, so if I give an input xk and del of n minus k, that is a particular sample of a signal of a sequence x of n. Okay, this is a sample of a sequence x of n. Okay, I am representing, I am giving a particular sample in a sequence xn. Okay, and for this one we are getting an output xk and hn minus k. So here it is satisfying the homogeneity property. Homogeneity property. Okay, homogeneity property. Like this, if you give a different samples, okay, here the important thing is why we are considering like this, del n h of n. Every signal can be represented as xk and del n minus k. Okay, so k equal to minus infinity to infinity. So a sequence can be represented like this. Okay, a sequence can be represented like this. We have seen this thing in the already in the earlier discussion. Now if x of n is given to it, okay, if x of n is the input, okay, if x of n is the given input, the output is summation xk h of n minus k. Okay, with sum up all samples. We sum up all the samples and that gives x of n, and that x of n is given to the input, for the system. We are getting an output k equal to minus infinity to infinity summation xk h of n minus k, which is y of n. This leads to finding out an output for an input xn. We are getting an output yn if the impulse response is hn. So this yn is summation xk h of n minus k, where k equal to minus infinity to infinity. Okay, and this indicates that for this system you give, let us consider and this is the input sequence. Here was input sequence A, B, C. So 0, 1 and 2. Okay, this is your x of n. So this A is represented as x of 0 del n, and this B is represented as x of 1 del n minus 1, and this C is represented as x of 2 del n minus 2. Now I give a particular input, the value x of 0 del n, a particular value with strength A. Okay, for this we are getting an output, a particular output, let it be y1. Okay, now again I am giving another input x1 del n minus 1, which is an impulse B. So getting an output y2. Okay, next another input x2 del n minus 2, which is the value C, getting an output y3. The sum of these three leads to xn, and the sum of outputs leads to your yn. So if you know the output for the del n, which is hn, then obviously you can get the linear combination of all those individual outputs. You can get the output yn for the corresponding input xn. Okay, and this is called convolution sum. So in the aspect of signal analysis, for any signal x of n, if the system is a linear time invariant system, okay, you can apply the convolution sum. convolution sum to to observe output y of n. Okay, to observe an output y of n. So you should not confuse with the shifting property and the convolution. Okay, shifting property and convolution. Shifting property. So shifting property is x of n del of n minus k equal to x of k del of n minus k, and whereas convolution, so this is a property for regarding with impulses, x of n convoluted with del of n minus k, the result is x of n minus n naught. Okay, these are the properties of the impulses. Okay, an unit impulse function property. One is shifting property and another one is the convolution property. So both are different. Okay, both are different, the shifting property and the convolution. Okay. Let us see some problems. Let us solve problem 1. So consider x of n equal to u of n and another function h of n equal to 2 power n u of n. Okay, so what is the output? So for the h of n system, the given input is x of n. Let us find out what is y of n. Okay, as you know that y of n equal to summation of k equal to minus infinity to infinity xk h of n minus k, whether it is h or whatever it was. Okay. So we have to convert your xn and hn into the dummy variable representation k, right? So x of n is u of n, that is I am representing in the terms of k, the dummy variable k. So x of k, the function is this one, 0 1 2 3, an impulse, sorry, a step sequence, and hk is, it is a sequence which is exponentially increasing, 2 power n un. So 2 power n, this sequence is starting at 0 and it's exponentially increasing the value. The values will exponentially increase. Okay, 1 2 3 like this. hn equal to 2 power n, sorry, hk equal to 2 power k u of k. Okay, so these sequences I am going to apply for this expression. So I want h of n minus k. Okay, h of n minus k. So first we go for h of minus k, then we go for h of n minus k. Okay, so what is h of k? H of k is the time folding version of your hk, that is white. Okay, this is h of minus k. Now 0 minus 1 minus 2 minus 3. Then you go for the shifting, that is you simply add an integer n. Okay, this is axis of k. You simply add n for this time instant values. So okay, h of n minus k, for each and every time instant let us add some n. So for this one add n, for this one n. So n minus 1, n minus 2, n minus 3, like this the values. So this is the signal h of n minus k, which is 2 power n minus k and u of n minus k. Simply you can write like this. Okay, 2 power n minus k and u of n minus k. We use this expression in this summation. Okay. So we will use this h of n minus k and this xk, and you sum up all those values by using the expression your xk h of n minus k. Okay, where k equal to minus infinity infinity. Okay, so let us multiply this h of n minus k and xk for different k values, and these different k values, let us see that we have added this n for this time instance, and we don't know about what is n. So I am assuming that this n places this entire signal, this entire sequence in the left hand side. So by changing the different k values, okay, that is nothing but by changing a different k values means I am changing this n values. Okay. By changing the different k values, I am moving this expression from minus infinity to plus infinity. Okay, this one is up to minus infinity, this expression is starting at n towards the left hand side. Okay, slowly we shift this sequence to the right hand side to overlap with xk. Okay, so until 0 1 2 3 4, until n is equal to 0, okay, y of n equal to, so case 1 till y of n, till n equal to 0, n less than 0, there is no overlap. Okay, for n less than 0, no overlap between h of n minus k and x of k. So y of n is 0, that is product is 0. Okay, but when n touches 0, okay, when this n touches 0, there is another case, that is when n greater than or equal to 0. Okay, greater than or equal to 0, this is, so the sequence will be like this, and your h of k will be overlapping here also. This is the first point where the overlapping starts. Okay, 0 and n 1 2 3, okay, n minus 1, n minus 2, n minus 3. So for n greater than or equal to 0, from this case the overlap starts. Okay, from here onwards overlap starts. So definitely there will be the product of h n minus k and x of k. So what is y of n? So y of n is the summation, that is k equal to 0. The overlap starts at k equal to 0. Okay, at that instant the overlapping starts. Okay, so if you go for another shift, okay, this value will be, okay, this h of n minus k, this n value will be at the position here, and for another shift the position will be here, and for another shift the position will be here. So as you move on by shift, okay, by changing the k value step by step, the overlap will, the overlapping of different samples will increase. So for calculating that product between h of n minus k and xk, you take the summation k equal to 0 to n. Okay, why? Because we are getting the sequence like this. At some instant, the overlap will be like this. Okay, the overlap will be like this. So this will be n. So 0. So from k equal to 0 to n, the summation satisfies, the summation will happen for the product of xk and hk. This is xk and this is h of n minus k. Okay, so what is xk? Xk is, every time it is 1, which is the step sequence. And what is h of n minus k? H of n minus k is 2 power n minus k. Okay, 2 power n minus k. So let us solve this summation. 2 power n, summation k equal to 0 to n, 2 power minus k. And this one is a finite geometric expression, progression. So 2 power n, 1 minus 1 by 2 power n plus 1 by 1 minus 1 by 2. So you will get an value 2 power n plus 1, 1 minus 1 by 2 power n plus 1. And this holds for n greater than or equal to 0. So your output is the convolution between, that is y of n equal to x of n convolution h of n is 0 for n less than 0 and 2 power n plus 1, 1 minus 1 by 2 power n plus 1 for n greater than or equal to 0. So this is the output. This is the convolution output for the given two functions xn and hn. Okay, like this you can solve the convolution between any two sequences with the above procedure. Okay, so let me discuss another one. X of n equal to 1/3 power n u of n, and h of n is u of n minus u of n minus 3. Okay, so 1/3 power n, this one is exponentially decaying sequence like this. So I'm directly writing in k 0 1 2 3 4 5 6. And what is h of n and u of n? U of n minus is subtracted from u of n. So you know about u of n, a step sequence 0 1 2 3 4 u of n, and u of n minus 3 is a sequence starts from n equal to 3. Okay. 4 5. So this is u of n minus 3. So if you subtract these two, you will get a finite duration sequence in the range of 0 1 and 2. So a finite duration sequence 0 1 and 2. This is your h of n. I am subtracting u of n minus u of n minus 3. Okay, so let us convolve these two sequences. So now again I am shifting, sorry, I am time reversing and shifting h of k. So I'm directly writing as h of n, sorry, h of minus k. H of minus k is like this, 0, minus 1 and minus 2, and now I am adding n. Okay, now I am adding n. So h of n minus k. So this is k, this is k, and here it is n. So this one is shifted to some position, n, n minus 1 and n minus 2. So let us overlap these two sequences. Okay, these two sequences which are 1/3 power k and u of k, which is exponentially decaying. 0, 1, 2, 3, 4. So case 1. So till up to n less than or equal to 0, not exactly, up to n less than 0, okay, no overlap. Okay, I am shifting this h of n minus k from left hand side to right hand side, that is from minus infinity to towards a positive axis. Okay, no overlap. So y of n is 0. In the case 2, so here you should observe properly. In the case 2, there is an overlap between limited impulses only, limited samples. It is, so this is your 1/3 power k, and when this n touches, okay, from n equal to 0, okay, when n is equal to 0, the value will be like this. The overlap will be like this, 0, 1, 2, 3, and again n, n minus 1, n minus 2. Okay, for n equal to 1, again for n equal to 1, there is an overlap of 2 samples. For n equal to 2, the overlap of 3 samples. Okay, so you have to write this one as y of n equal to summation k equal to, the overlap starts at k equal to 0, okay, k equal to 0 up to n only, okay, up to n only. Why? Because the overlapping will be up to like this. The overlapping will be when n equal to 2, okay, 0, 1 and 2, n, n minus 1, n minus 2. Okay, so up to this type of overlapping, you have to consider the 3 products, that is for n equal to 0, n equal to 1 and n equal to 2. So you take the summation from k equal to 0 to n only. Why? Because after k equal to, after n equal to 2, that is after when n is touching 3, the product will be different compared to this point. Okay, so here 1/3 power k, which is equal to, into 1. Okay, and this is 1 minus 1/3 power n plus 1 by 1 minus 1 by 3, and this starts at n equal to 0, and this will be up to n equal to 2. Okay, this expression holds from n equal to 0 to n equal to 2. So for n greater than or equal to 0 and less than or equal to 2, okay, up to for these 3 points, n equal to 0, 1 and 2 only, this y of n holds. Okay, and if you simplify this one, this will be 3 by 2 let us take the common 3 by 2 minus 1 by 2 and 1/3 power n. You will get an output like this, y of n. Okay. In the third case, case 3, the case 3, the overlap will be same, that is, this is, sorry, this is your xk, that is 1/3 power k, and after n equal to after n greater than 2, that is 3 2 1 0, that is n minus 1 n minus 2, from n greater than 2, that is from 3. Okay, from 3, from n equal to 3 or n greater than 2, the expression will be y of n is summation that will be taken as k equal to n minus 2 to n. Okay, this n minus 2, we don't know the exact position for the different positions, like if n minus 2 is 1, okay, and n value will be 3, and if you go for another shift, n minus 2 will be 2 and n value will be 4. Okay, so that's why for getting the generalized expression, you take the summation from n minus 2 to n, that is 1/3 power k. Okay, so for this one, the first term 1/3 power n minus 2 minus 1/3 power n plus 1 divided by 1 minus 1 by 3, the common ratio 1/3. Okay, and this is equal to 3 by 2 multiplied with 1/3 power n, 9 minus 1 by 3. So, and you're getting an expression um, 13 1/3 power n. So this is for n greater than or equal to, not equal to, n greater than 2. So y of n is 0, okay, for n less than 0, and 3 by 2 minus 1 by 2 1/3 power n for n in between 0 to 2, and the last expression 13 1/3 power n for n greater than 2. Okay, and this is the output y of n for the different n values. Okay, so I hope the convolution is clear for you by practicing these two different types of problems. Thank you.